Morning. It's the last class on plasticity, and we're going to talk about how to use ABAQUS to actually do isotropic and kinematic hardening. And it will be a lot of fun, this class. I hope you're almost done with your... I don't know what to say. Fun, I guess. Because you're not doing it at home either. So it should just be titled wherever fun, I guess. I hope you're almost, I'm sorry, what?
Fun work?
Fun work. That would be awesome. Let's call it that. I like that better than fun. So fun work. You're hopefully done with that by now. Have you been able to look at the incremental plastic strains, D epsilon, EP11 and EP22? Did you take their ratios with S11 and S22? See, the terminology gets confusing because ABAQUS calls the stress as S11, but you need the deviatoric stress, so you have to subtract the pressure from it and all of that. You did all of that. You found the ratios to be equal, so now you know how the flow rule is being applied and all of that. And we were so far working with an elastic, perfectly plastic material, and then in the last class, we introduced this material that undergoes hardening. We looked at isotropic hardening, and I told you that the surfaces keep growing. And then I introduced kinematic hardening and showed that the surfaces keep doing some other things. So what I want to do today is first show you how to build the model, and build the model using isotropic and kinematic hardening. And then I'll show you how to interpret the data, and then we'll get to see how these surfaces are moving and whether they're moving or that was just all a bunch of stories somebody made up and left in a book for us to read. Right? So that's the whole goal, and we'll get there. If we don't get through all of it today in class, I'll upload a second part to the video that you can look at later. I've not yet decided, but this looks like what's going to be the exam. So it's getting close to what we are going to be having for the exam. By now, you're very familiar with doing the analysis, pulling out the data, doing some manipulations in Excel and exploring it. So maybe I'll have you do that. I haven't decided yet because, yeah. Oh, it's a take-home exam. It's not never done in class. For those of you who are not familiar with Professor Varma, I rarely do classes in exams and classes. I just don't like the idea of being cramped by schedule. You can ask all my sponsors; they'll tell you the same thing, Mr. 1201, because it never gets done until it's 1 minute past the deadline. So unfortunately, that's true. So schedule will not be an issue. You'll have plenty of time to work on the exam. Have I done a in-class exam for a graduate course yet? Not that I can recollect. Okay, so this is the same model that we've been playing around with. It's by now you've become very familiar with it. It's a great model to study these concepts, and of course you can apply all of it in the end and be able to interpret the data. But what we need to do now is we need to define some new properties. And the way to do that is to go back into the material model, that's module number 2, and here you're seeing that the material properties have already been defined. But let me show you how I had gone ahead and defined them. Everything else is the same. There's the elastic material property. And last time you had added the plastic tab, and there was only one row when you defined it as an elastic perfectly plastic. You just said 50, 0. When you said 50, 0, it understood that you wanted a perfectly plastic material, which means that the size of the von Mises ellipse stayed exactly at 50. Now, we've talked about this before, that the true stress is given by the engineering stress multiplied by 1 plus the engineering strain, and the true strain is given by the natural log of 1 plus E. If you think about it, when you define a material that in engineering stress strain world is elastic perfectly plastic, then in the true strain world, it will never be elastic perfectly plastic, right? Because S is always multiplied by 1 plus E. As E keeps increasing, when you convert this into a true stress two-state work, you'll have a small slope. But when you gave that 50, 0, you told the software, I don't want that. I really want an elastic, perfectly plastic material. And that's why it never went above 50. Although you never told it that I gave you only the engineering stress strain curve, or that I'm not giving you the true stress strain curve. That's the command. It knows when you give it that second value as a 0, it knows I'm going to be in the elastic, perfectly plastic world, so I'm not going to convert the engineering stress strain into a true stress strain and have a positive slope. That's how it does that. But now that we are going into the world of hardening, we are going to have to use this. This was your home fun work number 2, where we had, and what we're looking at is an elastic bilinear material. I'm taking the simplest material. It has a yield stress of 50 ksi, and then it has a slope after yielding of 500. 500 ksi. I forgot to give that number for fun work number 4, but I had mentioned that we are doing the same example as in class. So a couple of you asked me, and I gave the number, that the strain hardening modulus was 500 ksi. But you use that 500 ksi, and in this case, I defined the material to go out to 0.03. That's engineering strain of 0.03. This was, of course, epsilon y, and this was the value of E equal to 29,000 ksi. So in order to define the material model in ABAQUS, I needed to first convert it into true stress strain, which it's easy to do. It's not difficult at all in Excel, right? The next step is to convert it into a stress versus plastic strain curve. Okay? That's also not difficult to do. And then inputting that stress versus plastic strain curve. And since it was just bilinear, I needed to enter just 2 points. The first point where yielding begins, 50, 0, and the second point is the stress and the corresponding plastic strain, 0.27. That's why 0.027. Therefore, that's why instead of being at 0.03, because we are only listing the plastic strain, it's 0.027. You see that? Yes? So that's how you would define. What have we just defined, by the way? I know we've given it the uniaxial stress versus plastic strain, but what does the software really need in order to solve the plasticity problem? It wants the effective stress versus effective plastic strain. That's really what you've given it in different words. Because they're working with a lot of people who are not familiar with the idea that you're actually giving it the fundamental effective stress, effective plastic strain curve. And if it were to tell you, I want the J2 value for this material, I want this effective plastic stress and effective plastic strain, 50% of the people would say, all right, where is the exit button on this? Close it. It looks dangerous to me. So it asks you for the uniaxial stress strain curve. And right here is the tab that asks you to select what kind of hardening you're going to go for. You can select from isotropic or kinematic, Johnson-Cook hardening, which I have not covered in this class. Of course, you can define your own hardening. I'd like to see that. Or you could use combined hardening, which will be some combination of the two, but we're not providing that. We haven't discussed that in class. So we'll either do isotropic or we'll do kinematic. Let's stick with isotropic to begin with. And so we're selecting isotropic hardening. And that's it. That's all you need to do to your existing model right now. And everything else will start chugging along with isotropic hardening now. And then, of course, you've defined the section associated with it and all of that. There's no difference to the assembly. The step, I just want to make sure that I'm saving the number of increments that I want. The incrementation, yes, I'm saving 100 increments in the second step. That means I'll have plenty of data. I should define that this is isotrop. So I remember, oh, this is the step description. This is where we apply biaxial stretching. Or maybe I'll rename it to just biaxial, because sometimes you'll do it in where you're compressing the other direction. I'll just call it biaxial. And if you look at it, our nonlinear geometry flag is still off. If we were to switch that on, we would have to take another course, 579, structural stability. Here's a plug. product placement. Step 1 is, of course, the uniaxial static analysis. Don't have to worry about that. The steps and everything are the same. Just going into the load module. And you remember all of these. We've talked about how these boundary conditions are set up, and you're using them now for your analysis. It's a lot of fun. You do realize that we didn't really need a detailed mesh, right? We could have gone with just element. There is no one element. There's no gradients or transients throughout the space of the finite element mesh. We're really just exploring how things are to be used. Boundary condition number 1, it's the same as before. It is the one which restrains the y displacement of the bottom edge. You're seeing that. I won't mess around with that. Boundary condition 2, I've switched it off. Boundary condition 4 is, I believe, the horizontal restraint on the vertical edge. We'll not worry about that. And then the 2 load steps. In step 1, I'm applying boundary condition number 5, as you can see. And what it is doing is it's stretching the plate in the x direction first to 0.6 inches, which is 0.5% of total strain. It will definitely produce yielding, but it will move in one direction. And then in the second step, I am applying, of course, 1.8 inches vertical displacement, which is going to apply 1% strain in the vertical direction. And while I'm doing that, I'm also increasing the x-axis displacement to about 1% strain. So that's the biaxial loading condition. So everything else is pretty much staying the same. And now, of course, we have the mesh, which we don't really need a very fine mesh, as we said. I'll call it as a job. And I already did that yesterday. So I will just override one of these. I will write funwork 5.2 isotropic, and I'll submit it, and it will say, okay, can I overwrite? Okay, I hope it works out. It should take only a minute to go through that analysis. We are using my server, so it should go fast. Do you have any issues with speed of analysis when you're doing this homework? The problem is very simple. There's nothing to worry about in terms of taking time for convergence and so on. So it's completed the first step, looks like. And it's almost done with the second step. Right. It's written all the data out. Great. So now we can post-process it. We can start looking at the results. And I can see that it has stretched as we had expected. Let me show you the results from step 1 first. So this is when you are at the end of the first step. You've got stretching in only one direction, as you can see now, more clearly. And at the end of the second step, you've got stretching in both directions, as you're seeing there. That's nice. We can look at the strains, make sure that the strains have followed what we wanted them to do. For that, we'll look at E, and we will look at E11. It'll be a contour plot, and it's all sitting at 1% strain, as you can see. Maybe I'll make this numbers a little bit bigger. So we can at least look at what we are doing. Okay, so that's where you're looking at the strain. It has done what we had asked it to do. You can look at E22, sitting at the same value of strain. Now we can look at S11. Let's do that. So S11 seems to be sitting at 59.93 at the end of the second step. I'm sorry, that's the Mises stress. Sorry about that. S11 is at 52.09 and S22 is at 65.49. Very interesting data there. Of course, I can look at the von Mises stress, and that's sitting really 59.93. It's really close to being at about 60. And I can, of course, look at the results in steps. So I can go back to step number 1, the end of step number 1, and see where it was. It was at 51.9 KSI in terms of the von Mises stress, which is the effective stress at the end of the first step. At that time, S11 was equal to 51.9, as you would expect. And what was S22? 10 to the power minus 13, because we were stretching it in only one direction. And then in the second step, as we applied stretching in the other direction, watch what happens to S22. It's moving very rapidly to 13, 17, 21, 25, and it keeps going. And it increases quite rapidly to that large number that we saw there. So something's going on. There's some plasticity going on. I don't really know what it means, but something's going on. So what we need to do is try and understand what's going on here. So what we'll do is we'll switch off some of these multiple states and start looking at the data. So in order to do that, what we'll do is we'll say result, I'll say tools, XY data, and I'll ask it to create some output. And I have it give me the values of, since it's a smooth output file, smooth mesh, I'll just take any one should be fine. And what I'm going to do is I'm going to pull out PE11, PE22, the two plastic strains in the 11 and 22 direction. I'm going to pull out PEEQ, which is the equivalent plastic strain. Then I'm going to pull out S11 and S22. I'm also going to pull out S-mysis. So I have all that information that I need. And I'll select any one element should be fine. I'm selecting that element, clicking done, and I'm asking it to save that information. And once that's done, I can dismiss out of there and I can look, all the data is here now. So what should I do? How should I make sense of what this analysis has done? So I can plot S11 and S22 first, and I see, okay, no, I wasn't expecting that. Were you expecting that? I don't know quite what to make of that. It seems to be telling me that S11 increased to 50 in the first step. Well, that makes sense. At the end of the first step, it had linear hardening, so it was sitting at some number. And then as I started going through the second step, I seemed to get this behavior that I didn't know what to do. And then S22 seems to be starting and peaking up, and there's some interesting stuff going on with S11 and S22. Don't know what to make of that. So instead, let me look at P11 and P22, see if that makes sense to me. And I'm looking at them now. All kinds of plastic strains. That's interesting. In the first step, I was getting plastic strains 1, 1, and 2, 2. And then in the second step also, I kept getting plastic strains. So is there any way for us to make sense of this data? You look at it and it's just data, right? You don't know what to do with it. So what I'll do instead is I'll say, all right, this is very good job, Mr. ABAQUS. Thank you for solving the problem. Of course, I don't understand what you've done, so thank you. So I'll say, let me see if I can make sense of this. So instead what I'll do is I'll say tool XY data, and I'll operate on the XY data so I can look at it a little bit better. And in this case, of course, I can port it all into Excel and do all of this. I'm just going to do it right now so we can look at it without going to Excel. And eventually we'll go to Excel. So we'll combine this. What we'll do is we'll plot the effective plastic strain versus the von Mises stress. And we'll call that, what should we call it? XY data 1. That's very imaginative. Isotropic. Okay. Clear the expression out, and let's see a plot what this tries to show me. What do you expect to see? It's the moment of anticipation. What do you see and what were you expecting to see? No. What were you expecting to see and what did you end up seeing? It looks a lot familiar in terms of what we had input into the model. It's giving me that bilinear behavior. There seems to be some issues going on right around here where I was writing a lot of data points when the system was shifting from one state to the other. But overall, it seems to be showing me this elastic plastic stress strain curve that I had input into the model. In fact, when I look at this, the effective stress, effective plastic strain is actually following what we had input. And at the end of the total analysis, we were very close to being at an effective plastic strain of about 2%. That makes sense. We had applied 1% and 1% in the two directions. So it should be somewhere around here. And the corresponding effective stress is hovering right around 60 KSI. So that makes sense, okay? I guess if I plot S11 versus S22, what will I get if I plot S11 versus S22? Let's see. What is S11 and S22? In this case, they are also the principal stresses. So if I plot them with respect to each other, what do I expect to get? Would I get the trajectory of the stress states in stress space? Is that what I would get? Okay. Let's see what that looks like. Does that make any sense to you? I mean, you've been doing the homework for the perfectly plastic material, and you've seen behavior. It looks nothing like it, or somewhat like it, but I'm not quite sure what it looks like. So how am I going to make sense of what's going on with this behavior in stress trajectory space? Well, clearly I won't be able to make sense of it right now. So what I'm going to do is I'm going to save the data, port it out, and I'll show you in Excel what this data really does. So I'll go to the report, and I'll write all of this information. I won't write these XY data 1 and data 2 because I'll plot them again in Excel. And of course, in the setup, I'll call it isotropic 1 in class. And that data has been written. I'll be able to port it into Excel and do some neat stuff with it. But instead of going to Excel right away, I'm going to instead do a few more analyses. What I'm going to do is I'm going to keep my isotropic model, and instead this time I will change the loading that I apply. I'm going to take this boundary condition, which was applying 1% plastic strain in the y direction in the second step, and I'm going to move it. What that means is that now, in the first step also, I'm going to apply biaxial loading. But I won't apply all 1.8 into it. I'll just apply what will be, I forget the number now. I guess I'll apply 1/3 of that. What is 1/3 of that? 0.6. If I apply. Is that what I did? I don't remember what I did. Give me a minute. So I'll be applying a displacement of 0.6 inches in both directions. And then, of course, in the next step, I will apply the total. I think I did not make that change. Apply 0.6 here. Why not? And then here, instead, I'll apply 1.8. So I've modified. So I've applied that displacement in 2 steps. So it'll tell you that you created the boundary condition in step 1 and then you modified it. So in the first step, both of them are being subjected to 0.6. Clearly, one side is longer. So the plastic strain for that will be shorter, smaller, right? Because it's 180 inches. So 0.6 divided by 180 is what? 0.00 something, 3333 something. So it's just got at the point of yielding, or it's gone just to 2 times epsilon y. And then we'll apply the rest of it. Good. I'll do this analysis again now, but I'll call it something else. I'll use this one. So I'll save that data too. And then I'll go back, do the kinematic, and run both the cases. And when I show you my Excel file, I may not have applied exactly the same. I don't remember what I applied in terms of that first step. I might have applied 0.4 instead of 0.6. So it may not exactly match up. But you'll forgive me, right? So now a completely different loading case, and I got the results. Well, it's a path-dependent problem. So I changed the path by which it got up to 1% strain in both directions. I changed the path how it got there, but I can still save all of that data. Now, usually what happens is I get confused when I start saving all the data in the same viewport. So I'm going to delete these since I've already exported them anyways, so I don't end up confusing myself. Especially in class. It's okay for me to be confused in my office. It's not okay. The same thing doesn't work out here. It would be very disconcerting to you. Um, so this time we'll pull out the same data. Pick any one element is fine. And now we'll create those two XY data that we created last time by operating on the XY data. We'll look at combining S mices with PEEQ, and then we'll combine S11 and S22 to see what they plot like. Well, this should be the same plot, right? We should get the same data back. That we had input. And then for S11 and S22, I don't know. I have no idea what to expect when I plot them with respect to each other, what they're going to look like. I sort of know, but it's nice to pretend that I don't. All right. So let's first look at the effective stress plastic strain. Well, that looks really neat. Since I had applied proportional loading in the first step, both directions had yielded. In the first step, I had applied stretching in only one direction. So there was an elastic component that was left when you apply forces in the two directions. Here, we've already stretched it out, so both the directions have yielded right off of the bat, and you get this nice bilinear curve that you'd put in back from your analysis. Of course, I can place the data points on there, and that's what it looks like. Very nice. The effective stress versus effective plastic strain that we had input, and if I plot S11 versus S22, wait. Okay. So what do I do with that? I stare at it for a few minutes and then I say, I guess it must have done it correctly, because I don't know what it means, right? So we'll have to decide what we're going to do with this. What is it doing? Does it make sense to us or not? We'll have to figure out what this is doing in stress space, because it seems to be following, it is telling me I'm following the flow rule. It's the associated flow rule. What does the associated flow rule say? The associated flow rule says that d epsilon ij plastic is equal to d lambda del f del sigma ij. And now little f is a function of sigma ij minus kappa squared, which is a function of the effective plastic strain. This is the shape of the curve. This is the size of the curve. Do you think its gradient is going to change? Del f del sigma ij will continue to remain Sij. So what you saw where the effective incremental plastic strain was proportional to the current component of the deviatoric stress. Current, not total, not in the previous stress, the current, S11 and S22. That will still hold because the gradient is still the same. The derivative of this is going to be still the normal to the yield surface wherever it's looking. What that means is, if I were to look at DEP11 divided by S11 and DEP22 divided by S22, should get numbers that are very similar to each other. So we'll see that as well. But this trajectory in stress space, I don't know what to make of it. We'll have to figure out what it looks like, what it is doing, and all of that. But before we do all of that, before we go into kinematic, I think we should save this data into something. Where should we save it? New file, isotropic 2. Okay, and now we're ready to go back to the material model and run these both cases again with kinematic hardening, because what we're trying to do is develop a better understanding of what's going on. What do these things mean? So instead of, I'll go back to the section definition, and instead I'll select the kinematic material. Are you okay with that? And the definition of that kinematic material, we'll edit it and look at it. Still the same elastic behavior, still the same plastic behavior. The data is identical. The only thing that has changed is this tab. where we've told, no, this is not an isotropic effective stress, effective plastic strain curve. This is a kinematic hardening, effective stress, effective plastic strain curve. So it knows now that it's kinematic hardening that we're asking for it. Everything's pretty defined. This is the step with the proportional loading, right? So we'll save that and submit it as a job, but this time we'll call it it should take it only a few seconds to go through that analysis. And then in the next, and the second analysis that I'll run with kinematic hardening will be where we just stretch it in the x direction first. So we'll have data for all 4 cases. Isotropic hardening with 2 different displacement cases and kinematic hardening with 2 different displacement cases. Looks like it's done. Now I wonder if the results are going to be drastically different since I've changed from isotropic to kinematic hardening. I don't know. So what I'm going to do is I'm going to start porting the data. And since I'm in the same viewport, it remembers what are all the things that I've been looking at. So I don't have to select the variables again. All I have to do is select the element. And I'm out of there. And now if I were to plot S11 and S22, I wonder what they're going to look like. Yikes. Something's going on with the stresses. Not quite sure what that is. If I look at the plastic strains, I can plot them. They seem to be increasing all the time. But what I really want to plot is the effective stress versus effective plastic strain. So what I'll do is I'll use the combine command. And then I'll do one more. I'll plot the stresses with respect to each other, similar to what we had done before, so that we can look at what the stresses are doing. And then now I can plot them and see what they look like. So that's my, oh, it looks exactly like what I had asked it. It does what I'm telling it to. It's staying on the effective stress, effective plastic strain curve. That's good. It's doing whatever it has been asked to do. That's nice. And then if I look at S11 versus S22 now, I don't know what that's going to look like. Hey, it looks a lot similar to what it did for the isotropic hardening. Of course, I don't know what that is and why is it doing yet. It's a mystery that I still need to solve as to what it's going on. And you can look at all the data and understand how it went from one point to the other. So that was in the first step, S11 versus S22. Does that make sense? Take a look at it. In the first step, S1 and S22 were both increasing until it hit yield, and then, boy, it went this way, and then it went that way, and then it went this way. Okay. We'll have to figure out what this means, and we'll do that. We have a tool. I've built a tool that'll help us understand what's going on. Okay. We'll go back to the load step, and this time we will edit the displacements. I had moved this, so how do I do this? I can't move it right, or can I? Gonna make me redefine that?
If you delete is left. If you deleted the modified one.
Can deactivate it. I can't delete it. I wanted to move right. There is a move right command, but it won't let me use it.
You the other ones left to run.
I don't let you do it.
Oh, thank you. How about that? And 1.8. Somewhere in there was a Microsoft programmer. Because I had to get out and get back in, and it worked. They have hired somebody from Microsoft, looks like. Because that's the charm, right? If it doesn't work, you just get out and get back in. Microsoft invented that. So we've got, in the first step, we're just applying stretching in the x direction, 0.6, that's about 0.5%. And then in the next step, we're applying biaxial stretching and all of that. It's still kinematic hardening, so we've got all that figured out. All we need to do now is submit the job. And it will be H5.2 kinematic, I think. Yes, we'll submit that. It shouldn't take more than a few seconds for it to go through. And then we'll port all of that data just the way we talked about. So we're about through 40 steps, 80, and then we're down to 100. So we're done. We can now, by now it's all, you've seen it all, right? You've seen how these things work, so it's boring by this time. But we have to go through the motions. We got to get rid of these first, otherwise they'll confuse me. So we'll, I'll delete these so I don't confuse myself, and instead I'll regenerate these. But by now you're seasoned individuals, so you're like, oh, okay, it's just doing the same thing. So I save all that data, and I guess what should I expect to see? I should expect to see the same things like I was seeing before. But let's go through the motions and complete that so we don't have any mysteries when we get to the Excel sheet. Let's plot the combined PEQ versus S-MISIS. And we'll save that as, and combine the stress states so we can plot those as well. And we'll save that as, and this is just momentarily so we can look at the results. All right, so the first one, I'm expecting the same thing that I had. Yes, I'm getting very similar behavior. It's trying to follow that linear slope. Right at the beginning of that second step, it has a big elastic component in that 2 direction because it's just starting to stretch in that direction. So if I make a plot of that, you can look at the data points and it will confirm that that's where it's happening. Right? You can see that now. And I can also plot the, I wonder what that's going to look like. Okay, it looks like very similar to what I had before for the isotropic. It's trying to do something. Need to figure out what that is. All right, so we've saved all the data. We can port it. What were we calling this? I think something like that. So we've ported all the data that we want. It's available in some drive somewhere, but how are we going to make sense of it? So in order to make sense of all of this, I built a little tool that would allow us to explore what's going on. And I built it in Excel. And what it's showing you here, so I'll explain a little bit what this does. I programmed the ellipse using the principal stress equation, sigma p1 squared plus sigma p2 squared minus sigma p1, sigma p2 is equal to sigma y squared. So this is where you give it the size of the yield surface, and these 2 points sort of follow the function. So if you look at any of these, they are always following, it's programmed. I've put in the sigma p1 squared. This takes the square root and solves that equation quadratically to get the corresponding stresses. And of course, it goes through all of them, and so you can, for example, change the size of the surface. You can say 60, and you saw the surface become bigger. Did you see it becoming bigger? You can make it 70. You can make it even bigger. You can make it 100, and you can make it really big. Or you can make it smaller if you want by just changing the size. So this is what I had meant by isotropic hardening. Let me move it out into a different, so you can look at it more clearly.
Can I ask a question?
Yeah.
What is the gray one that's all K1s? The series 1 plot that's all weird.
This one?
Yeah.
This one? You don't remember this one? Let me delete a few curves and you'll remember what that is. Didn't you just see it? That's why I built the tool, so it would plot out on the surfaces and show you how the points were moving. Let me bring everything back now. So it's telling you exactly what was going on. It's telling you that as the material was undergoing effective plastic strain, the sigma E value was increasing. You saw that it was linearly increasing. Sigma E defines the size. So every time it hits the yield surface, I can replot. That's 50 KSI. That's with 55. I've just copied and pasted. So those are the three curves. I have got the von Mises ellipse plotted for a size of 50 KSI, 55 KSI, and 60 KSI. And I ported all the data from ABAQUS. It's all sitting here. That's why you're not getting to see it. I've brought in the data and I've already pasted it and imported it and all of that. It's the same data. This is PE11, plastic strain component 11, PE22, PEQ, S Mises, S11, and S22. Those were the data that we saved. And all of that data from the two analyses with isotropic, it's titled Isotropic ABAQUS, is saved here. And this is a plot of the von Mises stress versus the effective plastic plot that we generated in ABAQUS and saw what it looked like. It's following that linear hardening slope that you had defined. And that is S11 versus S22 that we had from ABAQUS. And all I did was I copied it from here and I pasted it onto my beautiful isotropic yielding chart. And what it is telling me, this is the size of 50 KSI. That's when it first yields. That's the size 55 intermediate. That's the final size 60. So if you look at this load path, and for a second I'll remove this one. If you look at this load path, now you can see what's exactly going on. Depending upon how you've applied the loading, it was in the elastic range in that first step. S11 and S22 were following a certain ratio. And they went up, they hit the surface, and then they started moving tangentially to the surface. And they kept on moving tangentially to the surface. In fact, if I wanted to do a better job, I would probably plot this one at 54. Gives you a clearer expression of what's going on. Those data points are moving on that ellipse. But what happens here? Why does it go like that? Why does it do that? Because it's arrived at a point where the normal is moving that direction. Do you see what's going on? The stress state started from here. The stress state started from here, and then it moved tangentially until S11 and S22 became almost equal. It got into a state of biaxial tension, and then it just started growing linearly in that direction. Does that make sense? Each of these data points is the size of the yield surface. Each of those data points, we had 100 steps, and each of those steps corresponds to what? Each of those steps corresponds to a sigma Mises. That defines the size of the ellipse. So it's constantly moving on the ellipse. And as it is pushing in that direction, the ellipse is growing and it is moving right along with it. You can see the same by taking the other loading case that we solved, where we applied stretching in one direction first, then we allowed it to go in the other direction. Let's copy that and paste that back onto our same. There we go. And you see exactly what's going on. It hit the yield surface, then the point started moving on the yield surface until it got to a point where S11 and S22 had become almost equal. In which case, the normal to the yield surface is pointing at a 45-degree angle, and the points kept moving on those surfaces. So each of those points corresponds to a value of the size of the ellipse. Does that make sense? And what is that size of the ellipse? You can always look at it from your von Mises. So these are the various sizes of the ellipses as you're going through the yielding. They are growing from 50 to 55 all the way up to 60, which occurs right at the end. So I hope that helps explain what's going on for the isotropic hardening. The surfaces are getting bigger, the points are moving the way they need to in order to remain in a state of equilibrium. I wonder if the same will happen for kinematic hardening. But how do I program the kinematic hardening ellipse? Well, I did program it, and that's what it looks like. So here, in this case, I'm having to define, so what is kinematic hardening? Kinematic hardening means that the origin of the ellipse is shifted. How do I shift the origin of the ellipse? I shift all the points on the ellipse by whatever is going to be the shift in the origin. So I can specify the shift in the origin by coordinates A1 and A2. When I specify them to be 0, it's located at the center. And then as I start moving, let me give you an example of how the ellipses move first. So what I'll do is I'll move it. There you go. Do you see that? The sizes are staying the same, but right now it's moving only in the x direction. I can, of course, move it in the y direction also. And if I enter a positive number, it's moving downwards, which means that if I enter a negative number, it's going to start moving upwards. This is what we had meant by saying that the von Mises ellipse is just moving. Its size is staying the same, but the origin is moving. Well, how is the origin moving? Well, what's happening is, as you undergo effective plastic strain, it understands that sigma E has moved to a new number. But it also understands that this point, therefore, is anchored right here. But this is one numerical value. You could call it, this is the sigma E associated with kinematic hardening, the shift that has occurred. But it's shifting in S11 and S22 space. So how does it split this into the shift in the origin along the x and shift in the origin along y? That depends upon how the point is translating. So for example, when you're looking at a point, we move this to a bigger screen. So when you're looking at the point that comes and hits here, it's dragging the ellipse along its direction until the points start moving on it, and eventually it pushes the ellipse all the way out here. So when you're looking at, eliminate these so we can look at them one by one. So that's exactly what's going on. It's hitting the ellipse, and then it's moving along that ellipse until it starts dragging it along with itself. And the shift in the origin, like I said, you need two coordinates to define the shift in the origin. If we had kept pushing it in only one direction, there would have been only a shift in the ellipse along the x-coordinate. So imagine that we had kept stretching it in one direction. It would have just kept moving in one direction. But since we loaded it biaxially, it went in the other direction as well. That means that shift in the origin, the coordinates A11 and A12 together, the square root of A11 squared plus A22 squared will be equal to the total shift. Does that make sense? How much plasticity you have defines the total shift that you have seen. So if you had shifted out to about 55 ksi, you've got a shift of about 5. And that 5 needs to split up into two components in the x and y. That depends upon the path that you took. If you pushed it in only one direction, all of it would be going in that one direction. But if you pushed it in two directions, it would keep splitting and moving both in S11 and S22 space. And that's why I put in both the coordinates so we could see. So you're seeing that two load paths. This is the one where we went proportional loading, hit the yield surface, and then it started translating. And here what happens is the two stresses have become approximately equal, and the normal is oriented in that direction. It's pushing the yield surface along those lines. So if I take this green line, which is F versus G, and instead of specifying minus 10, I specify minus 5 and minus 5, you'll see much better comparison. So it's telling you how much the ellipses are shifting. Of course, if you take all of your plastic strain increments, which also I took a chance and looked at all of them, if you take your DEP if you calculate your incremental plastic strains and you calculate your deviatoric stress components and then look at their ratios, you will see once again all the numbers are 1 or very close to 1. So it's following the flow rule, it's moving on the ellipses, and it's telling you what the stress states the material are going to have. Isotropic and kinematic hardening did not make a very big difference. Why do I say that? Well, let's take one of these curves. Let's take, this is the curve from isotropic hardening, and we'll stick it on the one with kinematic hardening. See if there is a big difference between the two behaviors. Not much at all. The reason? We never reversed the cyclic loading. Monotonically, it won't make a big difference as to what you're... Of course, if we make this chart bigger and zoom in, yes, the numbers are slightly off, but not by a huge amount. In one case, though, the ellipse is becoming bigger, and in the other case, the ellipse is moving. But if you reverse the loading, you'd see more clearly as to the difference between the two. Similarly, if I grab the isotropic curve from here and paste it onto the kinematic, there is a small difference, but it's not significant. Monotonically, it doesn't make a huge difference whether I use isotropic or kinematic. Really, because the size of the surface is changing, which means that the normal to it is changing slightly. The size of the surface is changing, so the normal here as compared to the normal here is a little bit different. But the hardening is not significant. We're using a hardening of only 500 KSI. It's not like one surface is 25 KSI, the other surface is 50 KSI. We don't have such significant hardening in our materials. So the paths look very similar, but the paths can be understood by plotting them on the corresponding von Mises ellipses. This completes our entire topic of plasticity because we've covered hardening to the detail that I've never done before. So, I won't need to upload anything. I won't need to upload a second YouTube video. This should be sufficient. As to how we